In Chapter 10, you will study iterative algebraic solvers. For a given algebraic system AX equals B, where A is an n by n square metric and B is a vector in Rn, the iterative methods we'll consider can be formulated as in this equation. Starting from an initialization x0, we try to update the iterate so that the iterate xk is converging to the desired solution x. Depending on the choice of z, the convergence can be different. That is related with the eigenvalues of certain metric, so that we'll begin the analysis with eigenvalues and convergent matrices. In this section, some parts are quite simple, you already know, and also some other parts will be new. Okay, let's begin with very simple things. A is an n by n square metric. An eigenvector of A is a non-zero vector x such that Ax equals lambda x. Lambda is a scalar. In this case, lambda is an eigenvalue and x is the corresponding eigenvector. Once this equation is satisfied, then moving this into the other side, we have A minus lambda I x equal 0. This is a homogeneous equation. Now x must be non-zero. That means that this metric must be singular, which means again that determinant of this metric must be 0. So that equation is called the characteristic equation of the metric A, and this left-hand side is P lambda is the characteristic polynomial of A. The solutions of determinant of A minus lambda R equals 0 are the eigenvalues of A. Here is a claim. Lambda is an eigenvalue of A if and only if determinant of A minus lambda I equals 0. These are basic definition and claim. You may try to solve this problem yourself. Okay, now we have one more example. Find the eigenvalues and eigenvectors for the matrix. And now we can use the built-in function. For example, in Maple, by using the linear algebra package, we can find the eigenvectors and quite easily. Here, there is 2, 2, 3, and these are the corresponding eigenvectors. And also by using this command, we can find the characteristic equation. Okay, and you may try to find these eigenvalues and eigenvectors by using your pencil and paper. Okay, we have a remark. A is a square metric. Then the characteristic equation of the metric is the form P of lambda is determinant of A minus lambda I. Okay, that is minus 1 to the n, because here minus lambda. So once n is even, then you start with lambda n, but it's odd, then minus lambda n. So we can write in this way. And these are, except that one, these are the characteristic equation. Assume we have eigenvalues. Then we can write this portion in this way. Also, if we allow to have complex values, then this non-constant polynomial can be factored into linear factors. So we have that product, and by allowing the complex value to eigenvalues. Okay. Now, so if we try to get determinant of A, then that is the same as P0. Once lambda is 0, then that must be determinant of A. And here we have 0, so that is exactly this one. Now minus 1 n times, along with that one, minus 1 2n times. So we may ignore. And product of lambda I. This means that determinant of A is the product of all eigenvalues of the matrix. The spectral radius lambda A of a matrix A is defined by the maximum eigenvalue in modulus. And among absolute values of eigenvalues, we are choosing the largest one. So the sigma A, the spectral radius, is the maximum eigenvalue in modulus. We have a theorem. A is a square matrix. Then, now A2 norm is square root of the largest eigenvalue of A transpose A in modulus, and then take a square root. That's well-known identity. And for any matrix norm, the spectral radius is always less than or equal to the norm of A. That is a well-known theory. We can easily prove that. For example, now here the eigenvector, okay, lambda is an eigenvalue, and so we start with now A x equal lambda x, along with x norm is 1. We can scale so that the eigenvector length is 1. Okay, start with lambda absolute value, then now x norm is 1, so we reach it over there. By using the property of norm, lambda can go inside, but lambda x is the same as ax. Now we have this inequality, simple Cauchy-Schwarz inequality, or the norm has such property always. So that we reach it over there, but x norm is already 1, so here we have a norm. So lambda for any eigenvalue, its absolute value is bounded by the matrix norm. So quite simple. Okay. For convergent matrices, we have a definition. A matrix A, a square matrix, is convergent. The matrix is convergent if the power of A, as power increases, each entry is converging to 0. So AK in each entry is converging to 0, then we say the matrix is convergent. For example, we have a 2 by 2 matrix and half, 0, quarter, half. Okay, a squared, we have that. A cubed, again, we can get quite easily. a to the 4, okay, we have, in general, a to the k can be formulated in this way. The first component is 1 over 2k, 2 to the k, and 0, and k over 2 to the k plus 1, and then 1 over 2 to the k. As k increases, we know that all entries should go to 0, so that the given metric A is convergent. That is original definition. The power, and along with the power as increases, and each entry is converging to 0, then we say the metric is convergent. That is original definition. Now we have a theorem, and the following statements are equivalent. Such a theorem is called an equivalent theorem. An equivalent theorem is organized to expand the definition. So once A is convergent, then that is satisfied, again satisfied, everything will be satisfied. That means when we try to prove, or when we try to use the convergence, then now we can use any of these. So in a sense, such equivalent theorem is an expansion of definition. Okay. A is convergent, and also as n approaches infinity, a n norm is 0. For some natural metric norm, and for all natural metric norm, that means at least one natural metric norm, this is true, then for every other natural metric norms, it must be true. And yet, they are not easy to use in usual task, numerical analysis task, but this one is very useful. A is convergent is equivalent with this statement. The spectral radius of A is strictly less than 1. That means maximum eigenvalue in modulus is strictly less than 1. Power of A is converging to 0, or after multiplying x, any vector x, either way, and that original definition is original an is converging to 0. But now that one means that with the x multiplication is also going to 0. So either way, they are the same. But this one will be later on so useful. Okay. Okay, that's the end of the section. Thank you.